question going. Is it okay? What is the status? Stuff okay? Okay. So you managed to, okay, good. What about the assignment? Hello, Kelvin. What about your assignment? Assignment okay so far? Okay. Kelvin, how are you? Your assignment is okay? Okay, so today we're going to go towards, today is week 5. We're going to go towards this next chapter called link implementation. Okay. First thing I need to note down attendance. Word. Okay, if you can see, today's lecture is also very long, the usual very long lecture notes. So what we do is, as usual, okay, wait, let first thing is we need to check our cost plan. If you see our cost plan, hang on, I will show you that, right? In the meantime, let me just paste this. Okay, wait a second. I show you that cost plan. 352950. Okay, so we are in week 5. Week 5, we are supposed to, let me just show you the cost plan. Yeah, cost plan we need to always keep track of the cost plan so we don't go beyond or off track. Yeah, wait a second. Okay, now can you see that?
Okay.
This one is actually our cost plan. So look at the week, right? Week 1, week 2, week 3, week 4. We are in week 5. So looking at the topics, we have covered applications of abstract data types, ADTs. Okay, chapter 2, application of abstract data types. Okay, and then efficiency of algorithm. And then last week we did array-based implementation of ADTs. Okay, so this week we are basically supposed to do part of the array-based implementation of ADTs and as half part of the link implementation of ADTs. Okay, so because the lecture note is very long, what I will do is we will follow exactly what the cost plan is. So we will do half of the link implementation of IDTs, yeah, so that you can get a clear picture. So, but basically, this lecture is about linked list. I think you guys must be already familiar with this. It's just a recap of how you implement your linked list array-based implementation of ADTs in your coding. Okay, so this one, I will show you this chapter. Okay, so as you can see, we have millions, right? I added some as usual. Okay, so basically about 100, but of course some of the slides of images. It's going to be quite fast. And some of the items I add in also because so that you can have a clear picture of what it is actually talking about if you were to refer your lecture notes. Okay, do you have your lecture notes from the previous lecture, which I, for my version?
Oh yeah.
You do? Already, right? I already submit, I already include that in your email, forwarded that in your email. Okay, so keep that, do keep that, okay, as your reference, yeah, because uh, the lecturer will be giving you only the notes which are inside of your coursework, which is inside your Google Classroom. That's the standard. Standard means that without any illustration and some extra notes, but for me, I have to add in so that you can understand, right? But that is what we do. We need to make you understand. Okay, so without further ado, we will continue with our lecture. Same thing, I just turned off my video so we don't have any lag and whatnot. Okay, slideshow. I think this should be easy for you to remember because we're just having to recap. Okay, so chapter 5, link implementation of collection ADTs, right? First thing is bringing you back to recap. What is array? Remember the previous lecture we touched on array, all right? How do you make an array bigger? How do you add the array so that it can accommodate another element to be entered into the array, right? So here it says, what is the problem of array? Limitation. Overhead due to shifting during add and remove operation. So remember when you want to add an array, there are several methods which you can do that, right? First is to basically change the size of array um, uh, using the, you when you add that element in, it will automatically change. Okay, so another one is that will when you add the array, it will simply create another larger by expansion, expanding the array by power of 2. Okay, so basically you are transferring. There's a code that allows you to transfer your old array in the old what do you call that, the size into a larger double size. So that transfer is basically its limitation as well for this particular array because the incur costs, I mean, more operation, more ability of the uh, computer to support your array or any operation of your program that incur costs. So overhead due to shifting during add and remove operation, inflexibility due to fixed array size. Okay, so if array size insufficient to expand array dynamically, a new array has to be allocated. Okay, you create another array so you can transfer the old content to the new array. Okay, so if array size is too big, space wastage as only a small part of the array is utilized. Okay, so this is the limitation of using array. So there's a question here. Is it possible to have a flexible data structure? Meaning that you want to allocate space. Yes, this question is basically the details which is there is basically what you want to solve for the question above here. Is it possible to have flexible data structure? You want to allocate space. Basically, you need to create an object for each entry at the point where you can actually add the entry, number one. The allocate space when the entry is removed, number two. For add and remove, instead of shifting, which is referring to your array, shifting your old content of your elements in the old size into a larger content with a power of 2, or just adjust links between the objects. So these are the things that you can do, okay, to counter react towards this question. Is it possible? to have all these what you call it features. The object would need two parts, okay, for add and remove instead of shooting. Okay, the object would need two parts, one for the data and one for the link to the next object. Okay, so pay attention to all these features. These basically trying to answer this question. So what are these features all about? These are the feature of your linked list. Yeah, your linked list. So for your learning outcome in this chapter, at the end of this chapter, you should be able to, number one, describe what are the link structures. Okay, I believe you know what is linked list, right? Link structure. Linked list is linear and also non-linear, right? So list is linear. Linked list is basically not linear. It's a non-contiguous. Yeah, it's not. You can actually add, append, delete in any other places of the node. Okay, we're gonna learn that in a second. Next one, implement the ADT list, stack, and queues using link implementation. Okay, so this is also along the lecture notes. There is illustration of how you represent linked list, ADT list, which is referring to stack and queue using link implementation. Okay, right. Next one, evaluate advantages and disadvantages of a link implementation of linear collections. Last one, describe and implement variation. There are many kinds of variation of link structures. What are those? I believe if you have scrolled through your notes, you'll see that there are some. Okay, so next one, analogy for link data. So before we go towards the next slide, this is basically to show you a connection between how you connect that in the real life example with your linked list. Okay, so this is analogy for linked data. Now, given a situation of desks in a classroom, so these are the things that you need to do to the desks, right? You have to place it in the classroom as needed, number one. Each desk has unique ID, which is referring to address. The desks are linked by keeping the address of another chair, which is attached to the table or desks. And then, therefore, we have a chain of chairs. So, how do we illustrate that? Look at this. Figure 1, a chain of 5 desks. So, we have, if you notice, numbers behind the chair as well colored in blue, as well as the numbers which are on top of the desk labeled in bolded numbers, black. Yeah, so look at this. They are 5 chairs and table attached to that chair. Okay, so basically if you see 15, first on the back of the chair there is 22. Yeah, and then there are 15 on the table. Okay, this is representation of a link list. Okay, linked list has 2 nodes, right? One is the address, one is the data, right? So this is the data, this is the address. So, all right, next for the next node, the address of the first node will point to the next node. Okay, and then this will point, this one goes to here, this one goes to here. That means this next node has the address of the previous, this next node has the address of the previous. Okay, that is why you want to actually, why you have that, so that you can pinpoint your pointer towards which is the node that you have previously. Or you can see it this way, this is pointed towards this one coming from here. This one you can connect to this one. Yeah, this one connect to this one, and so forth. So this is a chain of 5 tasks, representation of data and node of each of the list. So here's the explanation. Forming a chain by adding the beginning to the beginning to beginning. First task, right, placed in a room, right? Hang on a second. Yeah. First desk placed in a room, blank desktop. right? This is the first node, the first list, okay, with a blank node. Okay, basically that is indicated that there isn't any next node yet, because in a linked list, the end of the node, right, is always null. Null means zero, so there isn't any. So you don't have any pointer leading towards the next node. So this is basically a representation of that. One desk in the room. So it's a blank desktop, no links, there's no pointer to the next one, and address to the first chair given to the teacher. Okay, you remember that there is a one node with that data address, yeah? All right, next one. So then after that, the second students arrive, takes a desk, and then this is to show address of the first desk placed on the new desk. So instructor remembers address of the new desk because that particular desk is pointed. This one is referring to this one because it is having the address of the next node. So this is basically link. Okay. So that is a second representation of new node being added in the linked list. Next one, another desk arrives. All right, new desk gets address of the second desk. So instructor remembers the address of the new desk, and then therefore it becomes the third list, the third linked list. Three linked desks, newest desk first. Okay, so this one has empty pointer. There is no address to the next node because that is the end, basically. Okay, right. So forming a chain by adding to n. This time the first student is always at the beginning of the chain. Okay, first basically linked list is implementing a method of FIFO, first in, first out, similar to list. Yeah. So this time the first student is always at the beginning of the chain. Instructor only remembers the first address. Yes. The address of a new desk is placed on the previous desk. Yes, remember that? So address of this place here. Okay. Okay, so that is at the end of the chain. Remember when I said end of the chain, always null for a linked list because that is the end. So it is no other node after it. End of chain found by following list, newest desk does not have a pointer address to another desk. Okay. Next one. So two linked desks, newest desk last. This is another concept because whenever we talk about a linked list, it has omnidirectional. That means you can add lists from the front, you can add lists from the back, you can add lists in the middle. So this is omnidirectional because it is not a contiguous, it's not referring to list. It is a linked list. Linked list has this special feature. Yes, so look at adding to the end. So two linked desks, newest desk last. All right, so this is a new one, the first. So you add from the front. Okay, is it the front? Adding by adding to n. Okay, at the end. Okay, so you add this going to be back, right? Like there, and then you add it to the here. The two linked test, newest test, last. Newest test, last. Yes, this is last. So, but basically you look as if it is in the front, but that is the last one. Okay, so newest test, last. Because this is the front. Okay, newest test, last. Okay. Next, three linked tasks, newest task, last. Again, you go to the last one. This is first, this is second, right? Newest task, last. FIFO. And the link goes on and on and on. The latest one going to that, looking as if it is in the front, but it is actually at the front, yeah? Okay, so forming chain by adding at various position. Like I mentioned, omnidirectional is a linked list. Okay, so it's not stored in contiguous data. It is basically omnidirectional direction. It can store in the middle, it can store in the front, it can store at the back. Yeah. So new entries may be placed somewhere in the chain, not necessarily at the end. Okay, so possibilities for placement of a new disk. Before all current desks, So this is the possibility of placing, meaning adding new list, linked list. Yeah, that is. So first thing, it can be added before all current desks, between all current desks, or between two existing desks, between, yes, in between, or after all current desks. Okay, before or after. Yes, so that is indicating that it can be added at various positions. So that is a chain of linked lists. This is concept, yeah, conceptual. Next one. Adding at various position is indicated by this example. So you have first desk is here, and then you have the second desk is here. So the this illustration is showing that you want to add it somewhere else, which is referring to here, beginning of the chain. Yes, you can do that. Okay, so this is the illustration of that, right? But reading of the first node is still being taken as this first indicator of the first test. Yes, the reading should still start from here, not from here, not from here. It still starts from here. Reading, yeah. If you write the code, the reading still starts from the first node. Yeah. Okay, so still adding it from various position. So this is beginning. Oops. Okay, 1425. So this has the pointer for that. This has a pointer for that, right? But that 14 will go to 20. Okay, then therefore this is no longer null because it is the reference to the first node because it has been added in the front. Okay, so that is that adding from the front. Okay, adding a new desk between is how you add it in between the nodes. So what is your first node? Okay, so new desk, the desk before is this, and this is the desk after. You want to add in between this before and after, so you add it here. So pointer automatically refers to the one which is inserted in between. Therefore, your next pointer is 12. Yeah. Next pointer for that which has been inserted will be 5. Okay. So just clear your mind and visualize this illustration. This is possibility of how a node can be added in a linked list before, after, or between. Okay. Now linked list. What is it? Linked list. A linked list is a collection of nodes that you know. Each node points to the next node in the list. Okay. So basically, the basic linked list is a linear linked list. Linear, that is the basic, right? Then you have linked list. Linear means sequential. So by default, arrangement is linear. But then after that, you can actually do addition, deletion in multiple places, in between, before, after. Okay, whereas a list can only do at the end, right? So you have a method called NQ and DQ. Yes, what is NQ? Item is added at the back of the queue. DQ, you basically remove an item from the front of the queue. Okay, so queue, this is the link implementation of queue. Queue definition of link, yeah. Okay, right. This is indicating the first node, right? There's an address there for the pointer. This is the pointer of the next node. So this is address. This is the pointer. Address, pointer, and at the end, this indicating a null terminated linked list. Okay. Sometimes when you write a note, right, you put that as a, yeah, null terminated. You represent if there is two, you have a, okay, I'm gonna go through that. I'm just, because I'm trying to bring you into the different kind of variety of linked lists, but okay, never mind that for now. Nodes are objects that are linked together to form a data structure. Okay, a node comprises of two parts. This is I mentioned earlier. This is for linked list. This is the structure, a component of the list. Yeah, this is a node. Each of the node has this data. Yeah, data part, link part. this is a pointer. In this data, there is a pointer which points from the previous node to this particular node. The link part will be that pointer itself that has the address of the next node. Okay, so that is a node comprises of two parts, which is the data part and the link part. Okay, next. Now the class node. When you write a program, you have a class node, right? So you present that based on these particular details. Okay, just as this, right? Data part, link part. Next. Yeah. So data is reference to the next entry in the list. Next is reference to another node. Okay. Reference to an entry. Entry means the node in the list. Reference to the next node. Yeah. So we have a code here. I will, I think, give it to you. As usual in your coursework, there's a lot of sample codes which you can refer to. Yeah, for this particular class node, you have node.java. Okay, so this is data. This is next. Next will be showing the pointer of the next node, which is here. Okay, so that is a structure. Now, 3 rules for linear linked lists. First thing, it has to have a external reference, or you call that pointer. This is a head pointer. Okay. To the first node in order to access a linked list. The last node must be null. Okay, this is a linked list. This is a basic linked list. Yeah. Other than the last node, each node next field must contain the address of the next node. So this is next field. Okay, each has the address of the next node. This has the address of this. This has the address of this. This has the address of this. But this doesn't have any other address of the next node because that is the end. There is no longer a node before, after that. Yeah, so that is a null. How do you add an element to a linked list in Java? Okay, so this is just an example of steps where you can follow, right? How you insert elements to a linked list. First thing, you first follow these steps. Insert at the beginning, allocate memory for new node. Okay, yes, you have to write a code for allocation of new node, means a new production of new nodes to be added in. That is completely new. Yeah, store data. Okay, and then change the new node to point to head. Okay, that means to the next node. Okay, that means you have this pointer to be set, and you first you set this one, you create a new node. It has to have this value and this value. All right, so this is the value data, this is the pointer to the next node, right? And then insert at the end. This is the beginning, right? This is beginning. When you add, this is what you should do. If you are adding it at the end, what do? Allocate memory for a new node number 1, store data, okay, and traverse to last node. Okay, last node means what? You have to set it to 0, right? Means you have to set it to null. All right, so insert at the middle means you are basically inserting a node in the middle. You've seen the illustration, yes? So you basically same thing, you do this, allocate memory for a new node, store data, change the next of your node to point to a head. That means from the middle going to the front. Okay, means not the front, after it. Okay, we'll point the address to pointer to the next node after that in the middle, right? Okay, so that is the how you add an element to a linked list in Java. So this is an exercise for you. Write a driver program that builds a linked list of strings containing 2 nodes as follows. Okay, so node 1, data. Next one is the pointer to the next one. So this is data, your data is data. The next node will be your data is structures. So how do you put this to append to the front? What would be the new structure? What would be the new structure? It's very simple. The new structure would just similar to this one, but the pointer would be this is placed in the front. you have? Maybe we can do that, right? Can you understand this so far? Noel and
Yeah.
Kelvin, can you understand so far? Yeah. Mm. So this one, can you understand what is the output would be if you want to put hang on, if you want to solve this question? Hang on, where is that thing? Trying to, okay. See here. How do I do this? I want to show you this actually. Uh, Let me show you a drawing, but second. So how do you put that? I love data structure here. Hmm? So basically, what do you do?
Put it in front.
Yes, exactly. Put it in front, right? The same thing. I'd want to illustrate that actually by like it's kind of tedious, right? So put it in front, okay? So you put this, I love, I would be replaced by this, love would be replaced by this. So basically, you append that, and that I will point to love, love will point to data, data will point to structures. Yes, you got it? So you have node 1, node 2, node 3, and node 4. Okay, so that is your new list. All right. So add statement to the driver program to so that 2 additional nodes are added to the front of the linked list such that the following output will be displayed using a for loop. Okay, so for loop means you have to create a program for this, and add whatever it is you have for your loop for loop. But as a representation of this illustration, I love would be the same node this way, but you change that I here and this love here, and then you connect it, make it to the front, like, double of that. Mm, just like that. For example, yes, like such, right? So data would be I, this is love, data structure. So node 1, 2, 3, and 4. Pointer goes here, love. Love goes to data, data goes to structure. Okay, such as that. Simple as that. I think you got it. Yes?
Miss,
Got the concept, yes?
is this one of the
Yes?
ADT?
Yes. ADT.
No. Okay.
Yeah, we're trying to get you the concept of applying linked list ADTs. Mm. Okay, so you know the concept of this one, yes? Okay. All right, so next one. You know about linked list, right? You have encountered linked list before, right? I think we have touched on linked list before. But this one is just this is just a recap, I think, how you implement it. Okay, next. So review. After all you have learned, or you've been briefed a while ago, what is a node? What is a node? Node is so you have a node is basically like an object. You have to know that thing, yeah. What is a node? Node is an object that basically have a pointer, which has a data and a pointer. Mm, where is that? You need to know what is a node. Node is basically object that has the value of the first value and then the pointer which link to the next one. Mhm. Yes, okay. And then what is a linked list? First thing you have node, right? Then you have a linked list. linked list, basically a list that has that particular collection of node which has data and pointers of each of the node. Yes, so also linked list able to append data, delete data, add append data from multi-directional, which is from the front, the back, and in the middle. So that is a linked list. It is similar to a list, which is the basic linear list approach, which are contiguous, but this is a version that is non-contiguous because it can add data in the middle, at the front, and at the end. Okay, so that is linked list. What does a program need in order to access a linked list? Well, basically needs to have a pointer, right? Need to have a pointer which points out to which node to find, node to find as an address, and then another node pointer to the next node. What should the head reference contain if the linked list is empty? So if the linked list is empty, what do you have to put in the linked list pointer? The head reference would be?
Null.
Correct. What should be the next field of each node store? The next field of each node store, basically the address of the previous the node which is after that. Yes. What should be the next field of each node store? Next field would be the address of the node after that. What should be the next field of the last node store? The last node, basically last, indicating no longer there is another node after it, so you put it null. What does it mean to traverse a linked list? Traverse means you basically trying to find or trying to uh, scroll around, as you know, traverse. You want to find node by node, right? You have to find your path going towards to find node by node. So that is a traversing. So you're going to learn about traversing. How do you traversing? And what is the example of code you do for your node if you want to do traversing? How can you find the last node in a linked list? So that is a method of traversing. You are basically setting up what you call the algorithm to point towards the last node, and then that last node is equivalent to null. Okay, so that's how can you find the last node in a linked list. Okay, now this is the link implementation of list ADT. Okay, so I show you this a bit of video.
Hi, I'm Joe James, and in this video I'm going to explain how linked lists work and how you can implement a linked list in Java. Every node in a linked list has two parts. It has a piece of data and a pointer to the next node. As you can see, it's a simple integer, 17. Here's a sample linked list with 3 nodes. You can see that each node has a piece of data and a pointer to the next node, except for the last node in the list, which doesn't have a next node. So it simply has a null value there. Every list also has a root node. The very first node in the list is called the root. So our linked list, we have to store a pointer to that root node. Some of the operations we need to use in linked lists, we need to be able to get the size of a linked list at any given time. We need to be able to find a piece of data in the list, add it to the list, and remove data from the list. And I'll show you how each of these operations works. Let's say we want to add a 10 to our list here of 3 nodes. We're going to start by creating a new node. We put the 10 in the data space for that node, and then we're going to point our next pointer to the root node. Now our new root becomes the new node that we just created. Effectively, we inserted the 10 node at the very beginning of the list. Now let's say we want to remove a value. Let's remove 5 from this list. First, we need to find the 5. We always starting from the root. So we look at the data in the first node. Is that 5? No. We go to the next node. Is the data in this node 5? Yes. So this is the node we want to remove. And we're going to remove this node simply by changing the next pointer in the previous node, the 10 node, to the node we're trying to remove's next node. which is the 5's next. Now we've effectively removed the 5 node because it's no longer seen by the list. If we traverse the list, we'll skip right past this node, so we really don't know it exists. So that's how the remove operation works. So one big advantage of linked lists is that you can insert and remove items anywhere in the list without shifting elements, as you sometimes need to in arrays. So insert and remove are big O of 1, or constant time operations. Some of the disadvantages of linked lists: first, they're not sortable like an array is. Then they're also not stored in contiguous block of memory like an array. So traversing a linked list sometimes is much slower than traversing an array. And lastly, there is no index for the items in the list. So you have to traverse a list to find an element, which makes find a big O of n operation. Whereas with an array, if you know the index, you can locate an item with big O of 1 time. Now let's look at how the Java code works. So first we have a node class, which I set up as a private inner class. Every node has a next node and a piece of data, which is in this case an integer. I set up 3 different constructors: a no argument constructor, so we could just create a node; a 1 argument constructor where we can pass in a value but have a null next node; and a 2 item constructor where we can pass in both a value and a next node. So I have 3 different constructors, and they're all pretty simple. And then I have setters and getter functions for the data and for the next node. Now let's look at the linked list class. It's a public class, and all of its methods are public as well. Every linked list has a pointer to its root node, and it also stores the size of the linked list as an integer. I have a simple constructor that initializes the root node, and it initializes the size to 0. I have some test code here that I'll show you in a minute. We set up a set size and get size function, setter and getter for the size. These are very simple setting and getting an integer value passed in. The add function passes in a piece of data, and since we're going to accept duplicates in our list, we don't check through the list to see if the value is already in the list. We simply add a new node using that piece of data and the root node as the next pointer, and then we set the root to the new node. We increment the size of the list, and we return the new node. That's pretty much it. So it's a pretty straightforward add operation. The find function, we first create a node called this node for the root. And then as we iterate through the list, we can use this node to iterate the list. While this node is not null, in other words, while we're not at the end of the list, if this node's data is the data that we're looking for, then return this node. So we're going to return the node itself, not the value in the node. Otherwise, we're going to advance our pointer to the next node. This node is equal to this node.get next node. And if we iterate through the entire list and we still didn't find our value, then we return null. So we'll either return the node that we or null. So that's how find operation works. Now we have a remove function where we pass in a piece of data. We're looking for that piece of data, and then we're going to remove that node. Now, as you recall, every time we do a find operation, we need the pointer to the previous node as well. So we're going to use this node to find the node we're looking for. We also, each time we're going to have a pointer to the previous node that we advance as well. So this node starts out as root, and previous node starts out as null because there is no previous node to the root. Now we have a while loop similar to the find. While this node is not null, in other words, while we're not at the end of the list, if this node's data is the data we're looking for, then we're going to set the previous node next node pointer to this node's next node pointer. In other words, we're going to delete this node from the list. And then we decrement the size of the list by 1. And we return true because it's successfully deleted. And if this node is not the value we're looking for, then we advance the previous node pointer to this node, and we advance this node pointer to the next node. So in other words, we advance both those pointers by 1 through the list each time this check fails. And if we go through the entire list without finding the value we're looking for, we return false. So that is the remove operation. Now we have some test code up here that I'll show you how it works. We have a public static void main, which is a main function to test it with. We create a new linked list called LL. We print out get size, which when we start out with a new list, the size should be 0. And then we do ll.add 8. So we add a value of 8. Now the size should be 1. When we print out the size here, we should have a size of 1. Now we add 3 more items to the list. So we add 17, 5, and 10. These are the same values that we had in the PowerPoint slides. And then we print out find 17.getData. Now keep in mind this find returns the node 17. So if we want to print out the value that's stored in that node, we have to do .getData. So since 17 is in the list, it should print out 17. And then here we do a remove operation. We remove the 5 from the list. We print out the size. The size of the list was 4 up until now, so now the size should be 3. And then we do a print find 5, and we should get null because the 5 is now deleted from the list. So let's compile our code, and we'll run it. So the first time we get the size of the list is 0. The second time we get the size is 1. We do a check to find the 17, and we find it. After we deleted the 5, we see that the size of the list is 3. And then we do a find 5, and we can't find it, so we get null. That's how our test code works. So that wraps up my video on Java implementation for linked lists. I hope you found this helpful. If so, please click the like and subscribe buttons. You can find the code for this video on my GitHub site here. I'm Joe James. Thanks for watching.
Miss,
Yes.
is the number randomly generated?
Which one?
The linked list, the field,
The
the
field
header,
as in which header? Oh, okay,
the
that
data.
one. You mean the data which you set? I think that one.
Yeah.
How can you set? How did you set your? I think you should initialize your data, right, for integer. As in you have to. You can set it as in. How did you set it? As in, if you want to put it as automatic, you can set that, right? By doing an incremental, or you can, okay, there are two ways. One is to set it as a variable. You have to assign a variable for that. Another one is incremental, meaning there is one point of variable and then increment that variable. Get what I mean?
Okay.
Yeah, because usually if you want to, just similar to adding a number, and then if you want that number to multiply, to becomes to increase, then you add first you need to have initialized an integer, and if you want to set it as constant, then therefore you have to put a value. Otherwise you put a variable n, right? And note, yeah, so it's basically setting it to n or setting it to 1, as in the big O n or big O 1, as in the variable. But anyway, we're gonna look into that in here more further into the lecture. Yeah. Okay. Right. Where's this one? Okay, so class node as an inner class. Node is an implementation detail of the ADT list that should be hidden from the list's client. Therefore, you want to define node as an inner class. For example, you have a private as a private class within the class that implements the list. Okay, so this is how you actually implement the ADT list of being hidden, right? So first is you have a private class within the class that implements the list. Okay, node as an inner class inside that private class. Next one is data field of an inner class accessible directly by the enclosing class without the need for accessor and mutator methods. Okay, so what is the example? This is the example. Public class linked list. Okay, that is your indicator of T, which accepts any kind of primitive data types. And then you implement linked list interface again, right? Private node, first node. So that is your first node, private integer, number of entries in the list. So this is how you basically answer the questions of your whether or not you want to set it variable or not, right? Private integer number of entries in the list, and then you have private class node, and then the private T data, which supports multiple types of data primitive data types, which is the entry in list. Private node next, link to the next node, yes. Private node T data, again, this data equals to data, next equals to null, right? And then this is basically you put it into a private class node. Okay, so this is private node. T data node, this data equals to the data, and this is next pointed to the next one. So you are basically trying to traverse, going through one node within a class node. Okay, so this is a meaning of putting a class node in the uh, inner class as an inner class. So you already have a class, you want to build another class within that because you you want to have it to implement it within a class itself. You don't want to create it separately. Okay, so again, a linked implementation of ADT list. Use a chain of nodes to represent list entries. You need a head reference to store the reference to the first node sample of code. Uh, your questions about how to set that also is projected in this linked list.java, where the variable first node contains the reference to the first node in the chain. The first node contains reference to the second, and so forth. Okay, also illustrated in linked interface.java. Okay, so this is similar to the one which you have. I think you have this already, right? Linked list, link interface Java, because it says here that it's the same as the chapter 4. Did you have all the sample code from the previous lecture?
Yeah.
Yeah, you have this, right? List interface.
Yeah.
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 Okay. What about link list? Do you have that? I don't remember. I think not yet, right? Link list, but you have the list interface. But anyway, did I give it to inside your? Hang on, let's see. Did I give it inside your coursework, or did I give it to you? To check on that one, right? Okay, never mind. I will check that later. I think I give it in the code, in the coursework. Okay. Anyway, next one. So it says here this is a cheat sheet in pointer assignment. The outcome is that the LHS left hand side variable pointer will point to the same thing as the right hand side pointer. The following statement updates current node to the next node in the linked list. Okay, so current node equals to current node dot next. Okay, so this is your cheat sheet which you can use. How you're going to point from previous to the next one, and next one going to the previous one. All right, so this is basically an implementation of if you must know, this is a circular linked list that has both pointers side by side, left and right. But anyway, that one's later. Move on. Traversing. How do you traverse? How do you go through node by node? You are traveling across, traveling, breath wide width means going side by side, move along the list. Yeah, to traverse a linked list means you want to traverse the chain from the first node to the desired node. Yes, if you want to find a node. Okay, so use a temporarily nodes at one at a time. Okay, so initially it says here a set of current node to first node, so that you have to set this current node to first node so that it references the first node of the chain, number one. Next one, in order to move to the next node, you use this statement, current node equivalent to equals to current node dot next, until you locate the desired node. Okay, so those codes are all given here. This is an example I give you. How do you traverse a linked list? Displaying the content of linked list. Here you want to move from temp node to the next node and display content. So this is a simple uh, looping of how you find and traverse through the node when temp is null. Okay, so we reached, and then we know that we have reached the end of the linked list, so we get out of that of the while loop. So the output of this would be list elements are 1, 2, 3, and so forth. Yeah. So this is your traversing. You want to traverse from one node or to another node. Let's see, this is an example. Next one. This is how you add data at the beginning. I add in this one so you can have a clear picture of how you doing this steps, as well as the representation of that in your code. Okay. Uh, the notes did not give this, but I give it to you so you can have a clear picture of how you can do this. Yeah. So this is how you add in the beginning. You allocate memory. This one has already been mentioned right previously. You have to store the data, change the next node to the change next of new node. The next one is the pointer to the next one. Change head to point to recently created node. Okay, so basically you point it to the front, and the front pointed to you. Okay. Mm. And then next one is insert at the end. This is how you insert at the end. Similar concept, similar way. Allocate memory, meaning you create one node. You store data in there, which is referring to the what kind of data in that node. And remember, you have two partitions of the node, right? One is on the left, it would be your data. On the right would be the pointer. Traverse to the last node. Okay, change the next of last node to recently created node. Okay, that is how you insert at the end. So how you point back to the recently created node. This is the code, yeah. Okay, this is the illustration which is given in the node. This is how you basically implement the first node when you want to add beginning. A is basically a chain of node prior to adding node at the beginning. This is A. This is the first occurrence. And then after that, you want to B. You go to B after adding a node at the beginning. These are the nodes which has been added. The first node, this is a new node. First and new. So first node will go to the new node, and new node will go to you. So basically you sit here. Okay. All right. So that is beginning. Adding to the end of the list. Okay, this is before implementation. This is after implementation at the end. Okay, so basically this is your new entry. All right, and then you go pointing towards, means the address of this new node will go towards the first node here, and then the new entry data. Okay, so this is adding to the end of the list, which means that over here you will have the null value, which because you are the last of the list. Okay, adding to the end of the list still. Yeah, a chain of nodes A just prior to adding new node at the end, right? And then B just after adding a node at the end. B. Okay, so similar to the one which I have already mentioned. Okay, this is just adding to the end of the list. Can have a look on this one again, yeah. So this is how implementation of linked list, adding and insert from the middle. Okay, this now was adding from the front, adding from the back. Now this one is adding and insert from the middle. So this is similar concept of how the first previous one is allocated. You create a node, you add the data, you traverse the node just before to the required position of the new node, because you want to point out that pointer to the next node, and therefore you change the pointer to include the new node in between, right? So remember that illustration on the chair. So you just simply change the first node change into your new node change into the previous node. Okay, this is your example of your code. Okay. This is illustration given in the text, even given by the notes, yeah, the original node. Okay, I'm just simply adding this one so you can have an idea of how you illustrate that in your code. Now this one is the what is given in your node. I believe you have seen this. Yes, this is similar concept within the middle of just illustration of how it is implemented. A is basically presenting prior to node, adding a node between adjacent nodes. Yep. So you see this, if you notice, this is a new node. So what happened here? This will have the address of the next node, and this will refer the address of this node. Okay, that is in between. Now delete. This is a delete from a linked list. I added up this one as well from the beginning, from the end, and then from the middle. So this is the implementation of the code. Yeah, you have to look on that one. Yes, similar concept. This is searching. It does not give here, but I give this as extra. Maybe you want to do search of the linked list. This is how you search an element on a linked list. Yes. Okay, so this is your steps, and this is the code. All right, next one. After all that editing, deleting, searching, now you want to allocate memory. Okay, so when you use the new operator, you create instantiate an object at the time the reallocate assign memory to the object. Okay, and then when you create a node for linked list, we say that you have allocated that node. Meaning if you add a node, for example, that means you have allocated the node. Yes, you have given a new, you have requested a new memory to be given to a new object in the JRE. This is deleted already. JRE. Okay, next one is a video, I think. Oh, no. Okay, so removing an item from link chain. So this one is a possible cases because, like I said, linked list is has the ability to allow for removal from the front, from the back, and the middle. All right, so it has been given an analogy of the chain of dash illustrate in following slides. So this one you can just have a look on that one. Yes, what happened if you want removing of the first node? Okay, so a chain of dash just prior to removing its first dash. This is what happened before. This is after. Oops. After, yes. This is gone. So basically this becomes the first, and then that is a reference to the next pointer. First you have this, and then after you delete that first node from the front, right? Then therefore you have this. Yes, this one. Because remember, looking at this is a blur. That means it has been deleted. Okay, after deleting the first dash. Next one is removing middle node. An analogy, you have dash before, dash to remove which is in the middle because we have added in the middle. Now you want to delete in the middle. What happened? So this is just that. Very simple, yes. You remove, and then the first pointer will straight away point automatically to the next node. Okay. Next one. This is a removing before and after of removing last node. Yes. Before you have 5, 8. This is pointing to the last node. Notice that this is empty because that is indicating the last node is always null. This is not a circular linked list, so therefore it is no need to put the address of the previous or the consecutive next node. So therefore that is null. Okay, so then you delete that. Basically, that becomes the sole null would be allocated to this one, which is representing the last node because the last node has been deleted. So that becomes the last node. So pointer reference is 0. This is just an illustration of how you remove the first node. You have to have a look on that one. Yes. Okay, this one has already been illustrated in the chair version. So just look at that one. This is removing from interior node, which is in between, has been illustrated a while ago. There's so many times being illustrated, so you should be able to get it right by now. Next one, deallocate memory. After the method remove removes a node from a linked list, You have no way of reference to the removed node because that has been deleted. So Java runtime environment implements automatic garbage collection. That is, it automatically deallocates, okay, because now you have a new node, okay, you have gotten a new node. Now you delete that node. When you delete that, that basically there's a free space. That's where your word deallocate comes in. So automatically deallocates and recycles memory associated with the node so that there is no references to it. Then you have an extra memory for a next node if you want to create. Okay, no explicit program statement is necessary. Okay, that is just automatic, right? You don't have to put like you want the clear, so you have to a clear indicator of your program, right? So this is a sample code you have to have for this chapter. Linked list, run a Java, and for the client would be registration.java. Okay, I will give you in this one later after the end of the lecture for today. So efficiency of implementation of an ADT list. Remember your big O's representation? For array-based implementation, you have array list, and then for link implementation, you have linked list. So how does that represented in your, what do you call, big O notation representation? For add to the end of list, you have variable set for your array, because remember, this is what you asked a while ago, right? Whether you want to set it to predefined variable or you want to set it to n. Okay, so basically for array you need to set, yes, so that's why you have a variable there, o of 1, add to the end of list, add to the list at given position o of n. Okay, that is referring to not variable. Retrieving an entry, also a variable, yes, o of 1. For link implementation, okay, everything basically is not constant, you put an n value to it. Okay, so add to the end of the list is o of n. Add to the list given position o of n, retrieving an entry o of n. Okay, so that is the difference between array-based implementation and link implementation. Are we okay?
Okay.
So this is the comparing implementation operation, which I mentioned a while ago, between array and also linked list. Basically, okay, adding a new entry. This is just to reiterate on the thing which I have been illustrated here. Entry operation would be fixed array, fixed size array, fixed size array. Yes, array is always fixed, right? That's why you need to set the array element number. Sometimes you can set it to n as well, so that you can have the ability to expand. All right, linked list is always n. Okay, add new position, new entry. Okay, fixed array, you can add, you can set it to on to or variable. Same goes with linked list, variable as well as non-variable, which means constant as well as variable. Okay, remove given position o n to o of 1. Okay, similar to this one, o of 1 to o n. Replace get entry, contains, display, clear, length. Okay, all those are respectively constant, constant to non-constant, non-constant, constant. Okay, similar to this one, similar concept, yeah. But this one has the ability to set it to variable uh, and constant here, similar to that, yeah. Okay, so basically figure 9 for the list operation for two implementation expressed in a big O notation. Assuming that a fixed array size, that is the double array method, is never invoked. Okay, do you know what double array means? You are multiplying that with 0, you double that, you change location of the smaller or older values and switch it into the uh, bigger array size. Okay, so now we are only looking at, you are just changing, you are allocating constant or non-constant to your making the array grow bigger, larger, right? That is comparing implementation between fixed array and link. Okay, tail references. This is basically you want to reference your tail, which is going towards the next node. So consider a set of data where we repeatedly add data to the end of the list. Now what happened is each time the add method must traverse the whole list. Okay, so this is what happened in your linked list. It is basically the traversal of node happens like that. You cannot go left, right. You have to go traverse one by one into code. So solution, how do you do that? This is the problem, all right? So solution would be maintain a pointer that always keeps track of the end of the chain, right? So you always have to find a reference, maintain a pointer that always keep track of the end of the chain. Okay, that is a tail reference, we call it. For example, first node and then the last node. Okay, so link chain where a head and tail reference is always there. First node, you have the address for your first node, probably 100. This one would be a last node. That should always be there, which is because this is going to point out to the next one. Okay, so you have to actually just simply put a tail references for that in your linked list. Okay, so this is how you represent that in your node to make you understand what does it means. For a while ago, tail references. Private data fields need to add the external reference to the last node. Private node, first node. Okay, that is how you present first node. Private node, last node. And then you have number of entries you have in your node. Private integer number of entries. Okay. This is about a bit a lot, right? So, but we still have time. We can just finish up before the time. Then we will stop right there. The time, ends. Okay, now this is exercise. Examine the implementation of the class linked list given in the ADT folder. Which methods you would require? Which methods would require a new implementation if you used both a head reference and a tail reference? So this is basically answer is the method add, remove, and clear. Okay, which method would you require a new implementation if you use both a head reference and a tail reference? Basically, the methods add, remove, and clear. Okay, so that is where you basically implement the tail reference. That you need to know where is the end, you need to know where is your first, okay, and then after that you clear. Okay, so this is how you clear method. Constructor calls it public final void clear. First node equals to null, last node equal to null, because you have a linked list, which is similar to the basic linear list, basic list, yes. It doesn't have connectors to the last, it doesn't have connectors to the first. And then your number of entries will be set to 0. Okay, because that is a specified list. Means reference to the list as in like the basic list. Okay. Okay. So this is again tail references, which we have gone again and again. When adding to an empty list, both head and tail references must point to the new node. Okay. When adding to an empty list, both head and tail references must point to the new solitary node. Meaning, for a new node you created, there has to be a pointer head, okay, and then the end node with a node. Okay, when adding to a non-empty list, no more need to traverse to the end of the list because your last node points to it. Okay, adjust last node to the next node in the new node and last node. So this is referring to your like a circular linked list. Okay, so they want to traverse to going round and round and find it until it can find the node that you want, then it will return you that. Or otherwise it still go traversing without going towards the end. Okay, it's just simply going around in the middle without having to go in the end because you set that. Okay. adding a node to the end of the non-empty chain that has a tail reference. Okay, so that is after executing last node next new node A, after executing last node to new node. So you here you have last node. This is the new node. Okay, last node will point to the new node. All right, and then B, last node. This is the last node. New node will be having the data from this is the data for the new node, right? Last node will go for this if this is the n of that. After executing last node equals to new node. Yes, okay. You add in a new node, therefore that becomes the last node. Last node becomes the new node. Okay. Just play around with the data and the tail, so you keep changing it from becoming new node into, if it is located at the end, becomes last node. And then you keep changing the values which sits under here and here, which is your data and your pointer. Yeah, so right, looking at that one, yeah, just look at that. Yeah, okay. Pros and cons of a chain for ADT list. This is the pros and cons. The chain list can grow as large as necessary and can add and remove nodes without shifting existing entries, because again it is omnidirectional. You can delete from the middle, you can delete from the back, you can delete from the front. So you don't have to switch like how a normal list would be, how it has to NQDQ, right? So this one is basically more flexible. Pros. But this is the cons. Must traverse chain to determine where to make additions and deletion. You have to traverse node by node. Yes, still, if you want to do addition and deletion. Yet to retrieve an entry requires traversal as opposed to direct access in an array. Retrieving an entry requires traversal. Yes, you want to find a node. Basically, you still have to, like skim through. You have to move along and search. Yes, requires more memory for links, but does not waste memory for oversized array. For links, meaning that you can add the front, the back, the middle. So therefore, you still needs memory for that. Links, yes, but it does not waste, because sometimes, like in a contiguous, you will only be allocate that size of operation based on the one which is allocated in the memory. Whereas if it is non-contiguous, you can actually simply slot, and that memory is allocated for the number of how much memory that you need to operate that particular item or element which you have to insert inside your memory for that particular list. Okay, you get what I mean? Am I confusing you?
Okay.
Because right, this what I'm trying to say here. Whenever you operate something from your memory, you have to utilize memory usage. So that goes back to the concept of contiguous and non-contiguous memory allocation. Okay, that is in your operating system. If you go for contiguous, data element, is that when you put into, you need to have a specific fixed data value. Data value means looking at the memory of that particular data. So if you go larger, if you're larger than that, you're not going to be accepted to execute. If you have smaller, then you're going to waste time, not waste time, waste memory. So that is what it meant here. Requires more memory for links, but does not waste memory for oversized array, because this is basically non-contiguous. Non-contiguous means you can allocate based on your need. It is for compared to contiguous, where you cannot allocate based on your need because the memory allocation is fixed. Okay, so if you cannot understand that, you get confused, so leave it. We're just going to move on. Yeah, this is just to give you an extra information why it says here does not waste memory for oversized array. Okay, next one. Other variation of linked lists, you have linear or circular, singly or doubly, with dummy node or without. Okay, so I have a video here. All right, she is explaining this concept of singly linked list, doubly linked list, circular linked list, and double circular linked list. So, okay, I think we can watch the video and we will stop here until the next lecture. Yes.
We'll discuss these four types of linked list: singly linked list, doubly linked list, circular linked list, and doubly circular linked list. You can modify these linked list according to you. Fine. It's not like that these are the four types of linked list. You can do some modification in these linked list while implementation, and you can implement your own type of linked list. Fine. So first of all, we'll discuss what is singly linked list. Singly linked list is the most common used linked list. When you say linked list, it means you are studying singly linked list. In singly linked list, each node contains two parts. One is data part and next one is address part, right? And that address part contains address of next node, or you can say address of the successor node, fine. Or you can say in singly linked list, each node contains data part and a pointer to its next node, right? See, like this. See, this is a node in the singly linked list. It is having two parts. This is data part and this one is address part, or you can say this is pointer, right? Pointer to its next node, right? Now, if suppose a singly linked list contains three nodes, then how you will represent that list? See, so these are three nodes. Each node is having its own address in the memory, suppose 100, 200 and 300. And this node, the data part of this node is, suppose it contains 3, it contains 7 and it is having 8. This is what the address part, or you can say a pointer, or you can say a link to its next node. So this part contains address of the next node. Suppose this is the next node, address is 200. So here you will write what? 200. So it is going to point to this node. This contains what? Address of next node, that is 300. So it is going to point to the next node. And suppose this is the last node. So the address part of last node contains what? Null. You can say 0. It is not going to point anywhere. And the address of this first node is stored in a pointer, you can say head pointer or a start pointer, in which this address is going to be stored, right? So now this is going to point here. See, this is not a head node, it is a pointer only, because it is going to store only the address of this node. If someone is saying head node, it means this is the head node. It is not the node, it is just a head pointer or start pointer. So when you are going to write a program, then you are going to maintain only this head pointer. You can say address of the node, first node. Fine. See, this is what a singly linked list. See, why this is known as a singly linked list? As the name suggests, this is having only a single link. See, this is a single link only. Single link to its next node. So here in this list, only forward traversal is possible in the list. You cannot traverse the list in backward direction, because this is having only one direction, that is going to be forward. Or you can say in this case only forward sequential movement is possible. Now, how we are going to represent this node when you are going to write a program, that we have already discussed. I am going to write here. See how we are going to represent that. We are going to write struct node, a user defined data type, that is structure, fine. And in this node we are having two parts, data and address. So you can say int data, you can say any variable a or x or something like this, fine. Next is pointer to next node. So here you will write what? Struct node asterisk, and the name of pointer you can say next or link, you as you wish. So this is the representation of the node, right, in the program. Why I am writing here struct node, that I have already discussed in the previous video, you can check out there. Fine. See, now next is doubly linked list. As the name suggests, see, doubly linked list, it is going to have double pointer, 2 pointers. Fine. So in this case, each node is having 3 parts. One is data part and 2 address part, right? Or you can say each node is having data part and pointer to its previous node and pointer to its next node. 2 pointers would be there, right? Something like this. 3 parts would be there. This is a node. This is node in doubly linked list. It is having 3 parts. Data part. This one is you can say pointer 1 and pointer 2. So this pointer is going to point the next node in the list, and this pointer is going to point to the previous node in the list, right? In this case we are having only single pointer. In this case we are having 2 pointers. That is why we are going to call it doubly linked list. Fine. So now how to represent this doubly linked list? See. So suppose in this case also we are having 3 node in the doubly linked list. See, 3 parts would be there, and the data part suppose contains 1, 2 and 3 integer values. Now this pointer contains the address of next node in the list. Fine. In the sequence of elements, right? So the next node is this one, address is 200. So this part contains 200, right? So this is going to point here. Now in this also we are having 300, the address of its next node. So it is going to point here. Fine. Suppose in this part, the pointer 2, it is going to have null, or you can say 0, because it is not going to point anywhere, right? So now second pointer is pointer 1. This node is having this address part is having address of its previous node, but this is the first node, no previous node is there, so it is going to have null. And this part of this node is having address of its previous node. Previous node is this one, address is 100, so it is going to have 100. So it is going to point here, right? The link is from here to here. This is having address 200, address of its previous node, so it is going to point here. Fine. So double links are there, 2 links are there. One is in forward direction, one is backward direction. And in the last node there is no successor, no next node. That is why this pointer is having null. And in the case of first node there is no previous node, so this pointer is having null, the pointer 1. Now how we are going to represent the node of a doubly linked list when you are going to write a program? See, same types, data type would be there. We are going to define a struct node. Struct node is a data type, name of data type. This is user defined data type, right? Within this node we are having 3 parts now. So one is integer, you can say data part, right? And 2 pointers. So the type is what? Struct node only. So this is how we are going to represent it. 2 pointers would be there. One is next. This one is next, means you are going to store the address of next node. And previous, this is previous. This is going to store address of previous node, right? Why this type is a struct node? Because this pointer is going to store address of which type of node? Type of node is always we will write what address the pointer variable is going to store, right? So here pointer variable is going to store address of, not a simple variable, address of a particular node, and the type of this node is what? Struct node. That is why we are writing here struct node. This is how we are going to represent this node when you are writing a program for a doubly linked list, right? Now third one is circular linked list. See, circular linked list, as the name suggests, it is going to have a circle. So or you can say it is a singly linked list. The only difference is what? See, this is singly linked list. In singly linked list, this last node is having what? Null. It is not going to point anywhere. But to make it a circular linked list, what you are going to do, in the last node of this list, we are going to store address of first node, right? So now address of first node is what? 100. So here you are going to store 100. Now this node is going to point where? To the first node. So it is now a circular linked list, you can see. So you can say a circular linked list is a sequence of elements in which each element is having a link to its next element, and the last node or the last element is having link to the first element in the list, right? So this is circular linked list. Now last is what? Doubly circular linked list. When I say circular linked list, it means it is what? Singly circular linked list. Next variation is what? Doubly circular linked list. So that list is having properties of both doubly linked list as well as circular linked list. Fine. So how we are going to represent that thing? See, in this case, node is what? Node is having only two parts, data and address part. So in the program, we are going to represent the node like this only. Only difference is we are going to modify a little bit. In the last node, we are going to store address of first node. Fine. And address of first node is in the head part. So in the last node, you can say you're going to store whatever is in the head pointer. So now for doubly circular linked list, I am going to update this doubly linked list only, because it is going to have property of both doubly linked list plus circular linked list. Fine. So now here we are going to discuss doubly circular linked list. See, in this case, to make it a doubly circular linked list, see this is the next pointer of this last node. This node is going to point here. So this node is this address here. We are going to write down address of first node, that is 100. So here you are going to write down 100. It means the last node is going to point here to the first node. Fine. Plus one more thing. See, this previous pointer of the first node, this is going to point where? To the last node, right? So address of last node is 300. So it is going to store 300 here. The previous pointer of the first node. It means this is going to point here, right? This is now a doubly circular linked list. So in this linked list also we are having three parts of the node, data part plus two address part. So you are going to represent something like this only when you are going to write a program. Only you have to make a little bit modification for this and this. This we are going to discuss when we will discuss the operations performed on these linked list. So from next video I am going to discuss the major operations performed on these linked list, that is traversal, insertion and deletion operation on these type of linked lists. As well as we will discuss advantages and drawbacks of these type of linked list. See, singly linked list contains only one that address. Doubly linked list contains two address part. That is why it is going to use more space than singly linked list. But obviously this is having, doubly linked list is having some advantages over singly linked list. So that also we are going to discuss in the next video. Fine. So I'll see you in the next video. Till then, bye bye. Take care.
Miss,
Okay, very easy to understand, yes?
during the practical
Question?
later, can I ask briefly about the assignment?
Sorry?
During the practical later, can I ask briefly about the assignment?
Yeah.
Okay.
Practical, yeah? Because it's all after, yeah, assignment or anything else. Okay.
We will discuss these four types of linked list: singly linked list, doubly linked list, circular linked list and doubly circular linked list.
Okay, this one is about linked list with dummy node, yeah? This is also a list which you why you put a dummy node at the end instead of a zero null value.
Welcome to this lesson about dummy nodes and linked lists. At this point, you should remember how to build a linear linked list. Remember, each basic node contains a piece of data and a pointer to the next node in the list. So, what happens if you go to the end of the basic linked list and you want to go back to the first element? There's no way to do that. So this video is about dummy nodes, which can be used to make connections between the first and the last elements in the list. Essentially, a dummy node is an empty node that usually points to the first actual node. It has no significant data, but it contains a pointer to the first node with something inside. There are a bunch of different ways to use a dummy node, but for today we're going to use it to make the structure illustrated below, which is called a circular linked list. This structure lets us easily go back to the beginning of the list without starting over. It also eliminates some of the test cases that are harder to deal with in linear linked lists. As a side note, circularly linked lists can be formed without a dummy node and vice versa. This implementation just combines the concept of a circular linked list and a dummy node in one video. Great, so by now you already know how to construct and connect nodes together. So let's try applying this concept to some actual code. For this example, we'll start with a linear linked list and change it into a circular linked list, and both of them will be singly linked. Feel free to take a minute and pause the video to familiarize yourself with this implementation of a linear linked list. Then just continue the video whenever you're ready. So if we wanted to change this code to reflect the presence of a dummy node, what areas of the code would need changes, and what changes would those be? Take some time and think about your answer, and continue the video when you're ready to see a possible answer. Are you ready? Great! So first, we would need to add a declaration statement to create the dummy node. Now we would need to change the next pointers in the nodes. Our head pointer would need to connect to the dummy node instead of the first node. So instead of head equals 1, we would have head equals dummy. We would also have to connect the last node in the list back to the dummy so that the list will become circular. So instead of 3 arrow next equals null pointer, we would change this line to 3 arrow next equals dummy. Finally, because the dummy node was also dynamically allocated, we must absolutely remember to delete it at the end, just like any other node. So we would add the line delete dummy at this last part as well. Awesome! Now you know the difference between a linear linked list and a circular linked list. You also should know how to make either one by yourself and how to change a linear linked list into a circular linked list with the dummy node. Thanks for watching this video and see you next time!
Miss, is the language shown in the video, is it Java?
I mean, this one with the linked list with the dummy node?
Yeah, the language
Yeah?
used, is it Java?
Let me see. Usually I...
Welcome to this lesson about dummy. So this structure will be singly linked. Feel free to take a minute and pause the video to familiarize yourself with this implementation of a linear linked list.
Yes, right?
Is that in Java?
Hang on. It looks like C also, right?
Then just continue the video whenever you're ready. So if we wanted to change this code to reflect...
I think this is looking like C. But
C?
you can...
No.
Because it has to include this one. Yeah. But if you want to find implementation of this, there are many codes online for Java as well. Yeah. Okay. So, but one is just to give you what is a heads up on what is a dummy node, because in your lecture note you have a dummy node at the end of that variation of the linked list, right? Okay, so this one is a class linked list. Okay, so this is where you can find in your standard Java package java.utility contains the class linked list. This one I mentioned is the Java program, which I am going to share with you, which contains all these additional methods. Add first, last, remove. First is adding, next is remove, and then it's trying to find that node. Okay, so there's also Appendix 5.1 for diagram illustrating relationship between Java collection framework interfaces and cases. So this one is a link implementation. Yeah, okay, this is we reach towards the link implementation of by using the ADT's stack, right? So this is how it is represented: a chain of link nodes that implements a stack implementation of link, right? Link list. So this is how it is. Or these are the chain of the node, and then when it is represented as a stack, there's basically stack. What is a stack? Stack is using what method to end of entry? LIFO, right?
Yeah.
Yeah. So this is how you put it in. That n becomes the last one, right? And then last in, first out. Okay, so this is the one who's gonna top of entry of stack. The last in would be the last in, first out. Yes. So in order to make this is first out, that has to be entered the last. Yes, that's why this goes first from the back. This goes second. This goes third. So therefore, as usual, this will be the first one to go out, just as how it is supposed to be on the stack. Last in, first out. Last in, first out. Yes, this is the last that is entered. Okay. So that is array, right? The first node should reference the stack's top because that is the last one entered in the stack. Okay, so it's pushing. Pushing an entry means you arrange it in an order manner. Okay, a new node that references the top of the stack, which is referring to A. Okay, and then B is the new node, which is now at the top of the stack. Okay, last in, first out. Last in, first out. Yes, last in would be the first to come out. Push. Create a new node, basically push method. Make a new node point to the current top node. Make the head reference top node point to new node. Okay, this is a array, stack. How you pop, which is removal. Of course, it is A would be before the first node in the chain is deleted. Okay, B is the stack after. This is A before, then you remove on top, that becomes 0, and then you move on towards the next one, similar as the house stack should be. Okay, so popping, yes. So if the stack is not empty, assign current top node to a reference to be returned. Okay, so this one. If it is not empty, then point out that reference. Okay. Assign current top node to reference to the return. Make the head reference top node point to the next node. So this one you have that here empty, and then this one will become the next one. Top node becomes the next one because this is empty. Yes. Okay. Okay. Now that one is what do you call stack? Now queue. How you implement link implementation of queue ADT. What is a queue? Queue is one after another linear arrangement of order. So basically, you have the first node entry at the front of queue, and then you have the last node entry at the last of the queue. So remember that how do you do a queue? What is the basic way on how you delete a queue? You use the concept of adding and removal. Okay, so there you have what you call NQ and DQ. Okay, NQ is basically item is added at the back of the queue. DQ is basically item is removed from the front, right? So NQ add item at the back, DQ add remove item from the front. So basically, this you can implement this concept of queue to linked list. Okay, so use a chain of linked nodes for the queue. Two ends of queue are at the opposite ends of chain. So accessing last node is inefficient. So you need to keep a reference to the tail of the chain. So just like how a linked list would. In summary, place front of the queue at the beginning of the chain. Yeah, front of queue, beginning of the chain, reference. Back of queue at the end of chain with reference to both. Okay, so almost like a circular node. Entry at the front of queue, entry at the back of queue. So that is your last node, that is your first node. Okay, place a front of queue at the beginning of chain with the back of queue at the end of chain. Yeah, that's it. Reference to both. Okay. Adding to an empty queue. How do you add and remove queue? You add from the, well, where do you add it from? You add it from the back, right? And you delete it from the front. Okay. So A would, before adding a new node to an empty chain. Yes. So you have the new node, right? This is basically the first node here, and this is the last node. So you are in the middle. You want to delete this. Was it delete adding to an empty node? Oh, okay. Before adding a new node to an empty node. Okay. After adding to it, so that you have first node is here, last node is here, indicated this is a new node. There is nothing first. So then when you add it into an empty queue, basically this node has to be labeled into the successive addresses. Okay, so this would be the pointer head for first node. That would be a pointer head for the last node. Okay, that if it is in the linked list, that would be valued as null. Okay, so this is basically a pointer head which states the address of the data for that node. Okay, so this is just an illustration of how you're adding an empty queue. This is adding to a non-empty queue. Similar concept with your linked list. You just have to change the values of your pointer and your successive next value. Okay, A before adding to a new node, to the end of the chain, B after adding to it. Okay, so just change the pointer. This is again recap of your enqueue method, how you implement that. Okay, create a new node. If this is basically here, is that? Oops. Adding, yeah, this one. This is just illustration of that, and this is the explanation. Yes, we are going to go faster on this one because it's already mentioned. Yes, how you remove an entry similar to that. A is a queue of more than one entry. Okay, B is after removing the queue front. So again, you look at the how queue is being removed. Queue removing is from the removal of an item happens at the front. Adding an item happens at the back. So here you want to remove, so remove from the front, this one. And then what happened is your front node, your first node becomes reference to the next node. Okay, as usual, right? If you want to do adding, yeah, this is how you remove, right? Okay, adding, we have already touched on that. Remove the only entry from the queue. Only means that is the first and that just simply return your client deallocate the space, free the memory. Yeah. So A is a queue of one entry. This is the only sole node of the queue, yeah, in memory. B, after your removal of that, deallocate, and then you return to the client means you set it to clear, and then that becomes memory deallocated. DQ, if the queue is not empty, what? This is a elaboration of that one. Okay, right. No, this is not empty. This one. Okay, so that is DQ method. Okay, so basically this one a link implementation of a queue. You have to refer your ADT link queue.java. Again, I am going to list down all this and put it, give it to you so you can refer. Okay, the methods which include in the link queue would be enqueue, get run, dqueue is empty and clear. So why you are given all this program so that you can refer and clear your mind on how you're going to execute the ADT implementation of using linked lists with also the stacks and queues. Okay, so I think it's essential for you to get this. Don't copy, but you can use it and create maybe your new means copy means just get exactly the same thing, but you can modify. Okay, you got it? You can modify it. Yes. Okay, so just keep looking. We are going to look at your assignment later on. These are the sample code. Link queue, customer.java, wait line. This is for queue. Yes, queue. Okay. Iterators. Iterators is just how you are trying to create a loop inside your program. So iterators help in looping. If you want to traverse, you want to loop out until you find the right link list, until you find the right node, so you do looping or iterators. Okay, so defined as inner class of the collection of ADT. So it has a direct access to the ADT data field. So this is how you basically represent that in your code. So I feel like if you can use this T, it is more flexible in the sense that you don't have to actually define your integer, char, string, and all that, right? Because that accepts about anything of your value for your data. So this one is another illustration of iterator in linked list. I gave this example so you can understand. Okay, so here we learn how to iterate linked list using iterator. Okay, people call it iterator, so I said like iterator. Anyway, the first steps you want to follow in order to create this is you create a linked list. Number 2, add element to it using add element E. Remember this method? Number 3, obtain the iterator by calling iterator method. So your output would be linked list element, Delhi, Agra, Mysore, Chennai, and Pune. Okay, so there is another implementation of iterators in link. So you have provide a public method that returns an iterator to the collection. Okay, so this is how you write it in your code. Okay, so circular linked list implementation of queue ADTs. This is more of a continuation of the circular linked list. You know how it works, yes? You just have to, it is a linked list, but you just have to have a pointer which circulate until from the first pointer. This is the last node. The last node would be n, usually set to null, but in circular it's just having ability to connect back to the front, which means it is rotating in a circle. Okay, so circular linked list implementation of queue ADTs. Okay, last node reference to first node, you know that. Now we have single reference to last node and still locate first node quickly. No node contains a null because your node has been set to locate pointer to the first node. That's why. So when a class uses circular link chain for queue, only one data field in the class, the reference to the chain last node. Okay, only one data field, and that would be pointing to the first node. Okay, so this is again repetition again and again so you can understand. Yes, a circular link chain with external references to its last node that has more than node and has one. Let me see this. How many other? I think it's about time already. We stop. Yes, it's finishing anyway. So this one is a doubly link. You know what is doubly, right? Doubly is containing multiple pointers back and front, back and front. That means I can look at you, you can look at me back. I can refer to you, you can refer back to me, etc., etc. So okay, that is a more to make it more efficient. That is doubly. So how you link doubly link implementation on queue. So this is what you should do. Yes, it's similar to how you concept of the doubly. Next one, doubly link implementation of a queue. TL references, similar to that. Yes, this is just a concept on how you do that. Yes. Okay, so I think we are done. Okay, so done. So basically, review of your topic would be, for now, after you have seen everything, right, you should be able to actually know what are the kind of link, what are link structures? Yes, you ask yourself, what are link structures? Do I know what are the link structures? What about the nodes? What about the pointers? What about the data? How is it added? How is it removed? How is it searched? How is it traversed? Okay, what are the kind of linked lists available? What is circular? What is doubly? What is normal linked list? Yes, and then again, what is dummy node? So all those, yes. And how do I implement ADT list for stack and queue using link implementation? Same concept, but just following your ADT of stack and queue. Okay, adding up the function of that. Evaluate advantages and disadvantages of a linked implementation of linear collections. Linear, basically, it does not have any way on how to append data left, right. Left, right means left, front, back, and the middle. So that is quite rigid. It is working for linear, is working contiguous data. That means any data that has a require bigger value, bigger memory space, it does not implement. Whereas in a linked list, it is allowing omnidirectional, is multi-directional of the adding, appending, meaning adding, deletion, and traversing. Okay, you apply dummy data because you want to basically emulate your circular link. So just to ensure that the node doesn't end at the end node, which is 0. So you want it to be more efficient probably. You want to include a dummy node. But sometimes it can be quite complicated because, you will have to allocate another new memory for your dummy node. Pros and cons, right? Okay. Next, describe and implement variation of link structures. That one I mentioned already. You have a linked list, you have circular, you have doubly, and you have the one with or without the dummy data, dummy node. Okay, so that is pretty much sum up the whole of today's lecture. Are we okay? Or are we too much overload? Overloaded already data.
Still okay.
Yes, okay. Okay, so I think it's pretty simple for today's because it's just a recap on how you implement your queues, your stack, your linked list, variation of linked list, what is it about, and all that. And the codes that you can use, okay, example of how you add that. I think this it could be of a help if you refer to the lecture notes and also the example of sample code, right? So I will provide that as an example by the end of this topic, by the end of this today. Okay, hopefully I can find all that. Okay, so we do you have any question before that, or otherwise you can forward that in your next session, which is our practical.
Yeah, forward.
Practical, yes.
Yes.
Yeah. Okay, Calvin. Any question, Calvin?
Forward lah. Yeah.
So in that case, if there's no question, we will forward it to our practical session. There's a lot of time there. We can use that to discuss all issues. And therefore, with that, thank you for your attendance. I'll see you later at 2 p.m. Okay?
Okay. Thank you, miss.
All right. Thank you.